Hello everyone, good to see you. Today we're going to talk about datum feature. Why we are going to define datum feature. Whenever we want to do machining to make a component, we need to fix the component. How we fix it, what is the orientation, what is the location, where is the origin. In order to answer this question, we are going to define datum feature. And after the machining, again, we are going to control the component. We are going to measure the accuracy of the component. That's why we are going to define datum feature. For example, if I'm going to measure the perpendicularity of one surface respect to another surface, I'm going to say respect to. It means I'm going to define datum plane or datum feature. Perpendicular to what? Relative to what? Reference to what? In this situation, we need to define a datum feature. Datum feature attached to the part. As a designer, we are going to attach datum feature to the part. And also, we have datum feature simulator. Datum feature simulator is attached to the tool. For example, if you are going to use milling machine to make a component, this datum feature simulator is going to attach to the tool. And also for inspection, if you are going to use a jig, this datum feature simulator is going to attach to the jig. As it is known, when we do the machining, the surface of the part is not perfect. That's why we are going to define a theoretical exact plane as a datum feature. And some certain points of part are in contact with this datum feature. In the same scenario, the surface of the tool is not perfect. Some certain points of tool are in contact with datum feature simulator. Based on the shape, we can have reference plane, reference axis, reference point, or datum plane, datum axis, datum point. How we are going to define it? For example, here, by using this symbol triangle by lines connected to the box, and we have a letter inside the box, the name of A in this example, datum plane A is defined here. Some certain points are in contact with this datum A. Whenever we are going to define the datum axis, for example, for hole, as we can see here, or for pin, we can connect this symbol to the surface of the hole, or it can be connected to the leader point, this arrow, or it can be connected to feature control frame for the hole over the pin, as we can see here. Whenever we are going to use the side view of the pin, this symbol should be connected to the dimension. In this situation, we are going to define the axis of the pin as a datum axis. Whenever we are going to define the reference point or datum point, the same scenario, this symbol should be connected to the surface of that, let's say, a sphere. Let's talk about the concept of the datum plane or reference plane. As it is known, each component has 6 degrees of freedoms. In order to do the machining or inspection, we are going to eliminate all these 6 degrees of freedom by using some datum features. Here, at the beginning, I'm going to use just this fixed gray plane as a primary datum plane. In this situation, this part should sit over this gray plane, and at least 3 points should be in contact with this gray plane. What happened? It means this component cannot rotate anymore around x-axis here, cannot rotate around y-axis. If it is going to rotate around x-axis, it will be separated from this gray plane. It means we are going to eliminate rotation around x and y-axis. And also, it cannot move along z-axis. If it want to move along z-axis, this gray plane is fixed, and this component will be separated from this gray plane. By adding this primary datum plane, we are going to eliminate 3 degree of freedoms, 2 rotation and 1 translation. In order to eliminate the other degree of freedoms, I'm going to add this blue plane as a secondary datum plane. As we can see, it cannot move anymore along y-axis, and it cannot rotate anymore around z-axis. We are going to eliminate 2 degree of freedoms. But still, this component can move along x-axis. That's why I'm going to add the third datum plane as a tertiary datum plane with the green color. In this situation, at least 1 point should be in contact with that. In this situation, I'm going to eliminate the last degree of freedom. For the primary, 3 points should be in contact. For secondary, 2 points should be in contact. And for tertiary datum plane, at least 1 point should be in contact. As we have discussed, here at the beginning, I'm going to delete 3 degree of freedom and then 2 degree of freedoms. And lastly, I'm going to eliminate 1 degree of freedom. We call it 3-2-1 principle. Let's see the first example here. We have primary datum plane S, secondary datum plane T, and tertiary datum plane U, as it is defined here, S, T, U. S is primary. It means at least I need to have 3 contact points here. For secondary, I need to have at least 2 contact points. For tertiary, I need to have at least 1 contact point. It is not important which letter we are going to use here, A, B, C, S, T, U. The order is important. Why the order of datums is important? In this example, we have V as a primary, W as a secondary, and X as a tertiary datum plane. As we know, for the primary, we need to have at least 3 points in contact. It is here in the yellow color, we can see here. And for secondary datum plane W, we need to have at least 2 points in contact, as we can see here at the bottom left-hand side. And for tertiary datum plane, we need to have at least 1 point in contact, as is shown here. But if we consider 1 point in contact for secondary datum plane and 2 points in contact for tertiary datum plane, we have this configuration. If I'm going to compare this configuration with this configuration, we can see the height of the hole is not correct based on the figure in the left-hand side at the bottom, because W is secondary datum plane, we should have 2 points in contact. But here, the right-hand side, we have 1 point, and the height is not correct. That's why the order of datums is critical. It is important. Let's see this example. Here, in this example at the top, I'm going to define the axis of this part of pin as a datum axis. It is along z-axis, and for secondary datum plane, it is B. B is defined here. It is XY plane in this example, as we can see. What happened? At the beginning, we have defined the axis of this part of pin as a primary datum plane. We are going to eliminate 4 degree of freedoms. It can move along z-axis, and also it can rotate around z-axis here. Whenever I'm going to add the secondary datum plane B, I can see it cannot move anymore along z-axis. That's why I'm going to write 4-1 or 4-1-1 if I'm going to define another point here at the top as a, for example, reference point. It cannot be rotated around Z, and then we have 411 principle. We are going to eliminate 4 degree of freedom first, and then 1 degree of freedom, and finally 1 degree of freedom. In the last example, again, I'm going to define the primary datum feature as the axis of this hole. It means I'm going to eliminate 4 degree of freedoms. This component can move along this primary datum axis, and it can rotate around that. If I'm going to add secondary datum feature as the axis of this hole, I'm going to eliminate 2 degree of freedoms. That's why I'm going to call it 4-2-0 principle. Now we have talked about datum feature. Next time I'm going to talk about datum target. I would like to close this session for now, and I hope you enjoyed. Have a nice day. See you next time.